Hello bachcho, let's read the question. Which of the following statements are correct? Option A says, there exists a function f from closed interval 0 to 1 to r which is discontinuous at every point in the closed interval 0 to 1 and modulus of fx is continuous at every point in closed interval 0 1. Option B says, let capital Fx be a function defined as small fx multiplied by small gx. If small fx is differentiable at x equals to a and f of a is equals to 0 and gx is continuous at x equals to a, then capital Fx is always differentiable at x equals a. Option C says, if the right hand derivative of f at a is equals to 2 and left hand derivative of f at a equals 3, then function f is non-differentiable at x equals a, but will always be continuous at x equals a. Option D says, if fa and fb possess opposite signs, then there must exist at least one solution of the equation fx equals to 0 in AB provided f is continuous at closed interval AB. Solution शुरू करने से पहले let's note down the key concepts for this problem. The first one is the definition for differentiability. So a function f is said to be differentiable at a point say x equals a only if the limit x tends to a fx minus f of a divided by x minus a exists and the derivative at a is equal to the value of the limit. Now the second key concept is the theorem of location of roots. So consider a function. So if we have a function f from closed interval ab to r such that f is continuous and f of a multiplied by f of b gives us less than 0. The number is less than 0. See, two real numbers when multiplied with each other gives a negative number only if they have opposite signs, right? So fa dot fb is less than 0. Then there exists c in the interior of AB interval AB such that f of c will be equal to 0. We will talk about this theorem in brief while solving the problem. Now let's start with the solution. Firstly, let's talk about option A. So for option A, we want a function f defined on closed interval 0 1 to r such that f is discontinuous at every point in the domain closed interval 0 to 1, but modulus of f should be continuous on closed interval 0 to 1. So an example of a function which is discontinuous at every point in the domain is the Dirichlet function. The Dirichlet function is defined as f of x is equal to 1 for values of x lying in the set of rational numbers and minus 1 for values of x lying in the set of irrational numbers. So let's take the motivation from the Dirichlet function and define our function f from closed interval 0 1 to r such that f of x is equal to 1 for values of x lying in the intersection of rational numbers with the closed interval 0 to 1 and minus 1 for values of x lying in the set of irrational numbers intersection the interval closed interval 0 to 1. Now you see function fx is clearly discontinuous at every point in the closed interval 0, 1. Now, the modulus function fx will give us value 1 for every x in the interval 0, 1, which implies modulus function fx is continuous because a constant function is always continuous, right? So we have modulus of fx is continuous for every x in 0, 1. So therefore fx satisfies the conditions in option A. Now let's work out with option B. In option B, we have a function capital of fx equals to small fx multiplied by small gx function, where f is differentiable at x equals a and f at a is equals to 0. We also have g is continuous at x equals a. We need to check whether the function capital fx is differentiable at x equals to a. So therefore, to go with that, let's first evaluate the limit. So we have limit x tends to a, capital fx minus f at a divided by x minus a equals limit x tends to a, capital fx is defined as small fx multiplied by small gx minus capital fx is equal to fa dot fa multiplied by ga. Fa is 0, so therefore capital Fa is equal to 0, so therefore we have x minus a. Now further we have limit x tends to a. Here we can write fx as f of x minus f at a multiplied by g of x divided by x minus a, since f of a is 0. So now, since both the limits exist as f is differentiable and g is continuous, so we can split the limits. So we have limit x tends to a, f of x minus f of a divided by x minus a multiplied by limit x tends to a g of x, which is equal to, so this expression gives us derivative of f at a, and here we have, since g is continuous, so here the value is multiplied by g at a, and so therefore the derivative of f at a is equal to f dash at a multiplied by g of a, since f dash at a exists and g of a exists, since g is continuous at a, and so therefore the function is differentiable always. Now let's talk about option C. So in the option C we are given that the right hand derivative of function f at a is equal to 2, while the left hand derivative of function f at a is equals to 3. We are also given that f is not differentiable at x equals a, and we have to comment on the continuity of function f at x equals a. So firstly let's write the left hand limit of function a with its limit. So this limit is existing and the value is 3. Now consider a limit x tends to a minus of f of x minus f of a. So multiply and divide by x minus a. So we have limit x tends to a minus of fx minus fa divided by x minus a and times x minus a. Since this limit exists and this limit also exists, so we can use the algebra of limits for multiplication of functions. So we have limit x tends to a minus of f of x minus f of a divided by x minus a times limit x tends to a minus of x minus a. So this is equal to, so here we have left hand derivative of function f at a multiplied by, so here limit is 0. So overall we get limit to be 0, and so therefore we have limit x tends to a minus of fx minus fa equals 0. If we rearrange, this will imply that limit x tends to a minus of fx is actually equal to f of a. So what is this implying? So this is implying left continuity of function f of x. So that is, we are saying that if left hand derivative of function at a exists, then fx is left continuous at x equals a. That is, limit x tends to a minus of fx is equal to f of a. Similarly, we can prove that if right hand derivative of function f at a exists, then f of x is right continuous at x equals a. That is, limit x tends to a plus of f of x is equal to f of a. So let's call this 1 and this as 2. So therefore from 1 and 2 we have limit x tends to a f of x is equal to f of a from 1 and 2. So therefore, so what does this imply? That function fx is continuous at x equals a. Let's now talk about option D. In option D, we are given that f of a and f of b have opposite signs. That means one is positive and other is negative. And f is continuous over the closed interval a to b. Then there must exist solution to the equation fx equals to 0 in the interior of in open interval a to b. So this statement is the statement for location of roots theorem, right? There we had a function which is continuous over a closed interval, and at the endpoints we have the product as less than 0. That means to say we have fa and fb of opposite signs. Then we have a point C in the interior of AB where f of c is equals to 0. Let's try to understand this problem graphically. So consider a rough graph. So let's say this is x-axis, this is y-axis. Considering point A here and point B here, without loss of generality, let's consider fa to be positive. So we have f of a here, and f of b is of opposite sign, so that is negative. So let's say f of b is here. So the point for plotting is here, and here we have b comma fb. Understand that we want a continuous function. So graph of a continuous function is drawn without lifting our pen. So if we start drawing our graph, we will not lift our pen. If we do so, we then get a break point, that is a jump, and this denotes discontinuity. but we do not want discontinuity. And so therefore the graph will be drawn without lifting the pen, and while doing so, while going from the positive side to the negative side, we will cross x-axis, that is we get a solution at say c such that f of c is equal to 0, and that is what the statement of location of roots theorem is trying to say. So therefore option D is the exact statement for location of roots theorem, which is true under the given conditions, and so therefore option D is the correct option. Let's now check the options. So among the options, option A, there exists a function which is discontinuous at every point, but mod of fx is continuous at every point in the closed interval 0 to 1. So option A is correct. Option B is also correct. Option C, so we having that right hand derivative of f at a equals 2 and left hand derivative of f at a equals 3. So these are special cases, but in general, even if we had like right hand derivative of f exists and left hand derivative of f exists, but function is non-differentiable, then too we can conclude that the function will always be continuous at x equals a. Option C is correct. Option D is also correct, since it is the statement of location of roots theorem. So these are our correct options. I hope you understood it well. Best of luck and thank you.